Alright, folks, day 8 of our limit unit. More or less a review day, just kind of tweaking a few ideas that we've already talked about. And let's get started, because we've got like a million problems we're going to do. So problem number 1, find the value of a so that the piecewise function is continuous for all values of x. So remember, our technique here is to set the two one-sided limits of f of x equal to each other, and we're going to be looking at that x value of 2. So let's look from the left, and let's set that equal to the limit as x approaches 2 from the right. And to do that, all we need to do is set the top branch equal to the bottom branch with with 2 substituted in for x. And for some reason I'm losing some of my symbols, but that should say that, and there should be a comma there. So I don't know why that's happening. But let's go ahead and get going. So we're going to say that a times x squared is equal to 2x plus 1. But we're going to substitute in 2 for x. So I'm going to get a times 2 squared equals 2 times 2 plus 1. So we get 4a equals 4 plus 1, which is 5. And divide by a, and I can't talk, divide by 4 to get a equals 5/4. Problem number 2 says give an example of a piecewise function that is continuous for all x except for x equals 3. Well, any piecewise function that is not continuous at x equals 3 will work as long as it's continuous everywhere else. So let's just make something up like 2x cubed when x is less than 3, and 5x squared when x is greater than 3. That is defined everywhere except for 3, and it's defined by polynomials, which are continuous, so we're good. Question number 3, find the limit as x approaches 4. And it should say minus 4, and let's go from the left for this problem. I don't know why all my minuses are not getting included in this. I don't know. But we can do this anyways. Whoa! Remember that this is going to be our function that looks like that, and that's going to be x value of 4. And coming to the x value of 4 from the left, we're down in this bottom branch here, which has a y value of -1. So that is our limit. Alright, so let's find the limit of this little function 3 times e to the negative 0.2x. So think about what happens to negative 0.2x as x approaches infinity. Well, we're going to get infinity, which you can think of as a positive number, times negative 0.2. Well, that's going to go to negative infinity, because 0.2 times infinity is still infinity, but that negative will make it a negative infinity there. So we're kind of like thinking about 3 times e to the negative infinity. Whoa, that's crazy. But I want you to remember one thing. If you have an exponent, like say you have 5 to the negative 2, well, that is equivalent to saying 1 over 5 squared. If your exponent is negative, just move that entire term to the denominator. So you should think of this really as 3 over e to the infinity. And e to the infinity is just infinity. So really, this is going to be 3 over infinity. So 3 divided by a monstrously huge number. If you have a really, really big denominator like that, this is going to go to 0. So this limit, as x approaches infinity, of 3 e to the negative 0.2x is 0. And that tells us some interesting information about this function right here. Because now we're saying that this whole term goes to 0 as x approaches infinity. So that means this limit is just left with 500 over 2, which is 250. So the limit as x approaches infinity, this function, is 250. and 50. Remember, this is going to be the graph that looks like that, and it's going to level off there at 250. And we figured that out without a calculator. This is going to be a calculator problem on your test, but you can answer it quickly without a calculator, knowing what you know about limits. So let's answer a similar question now. What is the limit of this function? Notice that's the same bit from that denominator, but now we're looking at negative infinity. Well, now again, negative 0.2x, as x is going to negative infinity this time. Notice we're going to have a negative infinity times a negative 0.2x. Well, infinity times 0.2 is still infinity, but I have a double negative, so this time I'm going to end up with a positive infinity. So I have 3 times e to the positive infinity. And again, e to the infinity is infinity, so I have 3 times infinity. And 3 times infinity, oh my gosh, is still infinity. Do you notice how that's working? So this limit here is infinity. And now I'm going to ask the similar question. How does that then control the behavior of this function? Well, that's like saying we have 500 over 2 plus infinity, which is 500 over infinity, which again is 0. So this limit is 0. So that's telling me that the horizontal asymptote to the left is 0. So now I know I'm at 250 up here, and I know that's cruising down to 0 right there. The last question we're going to answer is this one. Limit as x approaches 0 of this function. Well, you can directly substitute in 0 there, and you're going to get negative 0.2 times 0, which is 0. So we have 3e to the 0. But you need to remember your exponent rules, because any number to the 0th power is 1. So I really have 3 times 1, which is just 3. And notice this is as x approaches infinity. So this is telling me essentially, if I were to think of this graph, it's telling me a y-intercept right there of 3. So apply that here. What does that tell us? Well, that tells us that this whole bit there goes to 1. So I can kind of ignore it. And this limit is going to be 500 over 2 plus 3. Well, 2 plus 3 is 5. So I have 500 divided by 5. So this limit is 100. And again, that is telling me that the y-intercept of this logistic curve is 100. And that top bit up there is 250. So clearly not a good scale there. And then that is down at 0. But I was able to figure out all of the information about this function without using my calculator. This will be a calculator problem on your test, but you can analyze it quickly instead of bothering with finding a good window on your calc. So sometimes it's not quicker to use your calculator. Alright, so let's find these two limits. Let's find this limit using what we just thought about on that last problem. So as x goes to infinity, if I have a 0.3x there, and really I think that it's omitting my minus sign there. I think that's supposed to be a negative 0.3x. So limit as x approaches infinity of this, we'll again recognize that that right there is going to go to negative infinity. So that's like saying 3 over infinity again, right there, instead of any of that bit, which goes to 0, so we get 500 over 2. Finding that horizontal asymptote is 250. But let's pretend like it did actually say positive 0.3x there. We'll think about how that's going to change the problem. As x approaches infinity of this, now that numerator is going to infinity. So I have 3 to the infinity, which is going to give me infinity, plus 2 is still infinity. So I have 500 over infinity, so that limit would be 0. It's essentially a horizontal flip there. So now let's find this limit, and let's use our calculator for this. But here is the deal. This is a trig function there, cosine. So you need to make sure that your calculator is in radian mode. So hit the mode button, which is to the right of your second button on your TI calculator. and go down a couple options and make sure that radian is highlighted instead of degree. Once you do that, recognize that we're looking at the x value of 0. So when we graph this on our calculator, we want to be looking pretty close into 0. So -1 and +1 is probably a good bet there for x. And go ahead and find it. You can probably do a zoom fit even once you've set up the x values. Now when you graph this on your calculator, you're going to want to enter this as y equals 2 cosine for x, close those parentheses, divided by, open a parenthesis, 15x, close a parenthesis, plus 2. And that will get you a graph that looks like that. It's weird. It looks like strangely 1 over xy. And we're finding the limit as x approaches 0. Notice from the left it goes down, and from the right it goes up. So this limit does not exist. Okay, let's find some values of k and m here that make these functions continuous. So let's look at this first function over here first. Remember the idea here, and I'm noticing that should be like that. The idea here with this one is that we need to make the limit of f of x as x approaches 2. We need to make that equal to f of 2, the value of the function. So we're going to set these two branches equal to each other. Let's factor this first, though, because we're going to get x squared minus 2 times, I'm a liar, we're going to get x minus 2 times x plus 2, and so we get those x minus 2's that cancel. So really we're going to have x plus 2 equals 2k, and I'm substituting in my x value of 2, so I get 2 plus 2 equals 2k, which is the same as 1 plus 1 equals k. Notice I just divided both sides by 2, and we get our k value of 2. Now let's do this problem over here. Same exact idea, except I have a k and an m, so I'm going to need to come up with two equations this time, but luckily I have two different x values that I can look at to make this continuous. So, equation number 1, let's use the x value of 4, so I'm going to get 4k plus 3m, because I substituted into that equation, equals 1/2 times 4 squared plus 1. So let's simplify. 4k plus 3m equals 4 squared is 16, divided by 2 is 8, plus 1 is 9. Let's go ahead and find our other equation really quick. Now we're looking at the x value of 8. So I'm going to get 8k plus 3m equals 8 squared is 64, divided by 2 is 32, plus 1 is 33. So kinda ugly, but that's alright. So now I have two equations here with k and m. So I want to solve this system of equations. So if you're super savvy, you can use a calculator and a matrix to do this. But if you're not, you can go ahead and do it by hand using substitution. So what I'm going to do is I'm going to solve both equations for 3m. So 3m equals 33 minus 8k. And this equation says that 3m equals 9 minus 4k. So now that I have these two separate equations, both equal to 3m, I can set them equal to each other to get 9 minus 4k equals 33 minus 8k. Let's combine like terms. I'm going to add 8k to both sides, so I'm going to end up with 4k over here. I'm going to subtract 9 from both sides. 33 minus 9 is 24. And so divide by 4 on both sides, and you will get that k equals 6, which is awesome, cool stuff. But now, even cooler than that, I can substitute k back in to find m. So I'm going to use this equation right here just because why not? And I'm going to get m equals 3 minus 4 thirds k divided by 3 there in both sides of that equation. And I'm going to substitute in my k value. So I'm going to get m equals 3 minus 4 thirds times 6. Well, 6 times 4 is 24, and 24 divided by 3 is 8. So that simplifies to 3 minus 8, and 3 minus 8 is negative 5. And that is my m value. Pretty cool little system there. Alright, so let's sketch this rational function. Ignore that thing there. Let's sketch this so we can find these limits. So again, to do this, let's factor this function. We're going to end up with x over x plus 3 times x minus 3, like that. So I'm going to get two vertical asymptotes at 3 and negative 3. I'm going to get a 0 at x equals 0. And I'm going to have a horizontal asymptote at y equals 0. No holes or any fun things like that. But now we can sketch this function. So 1, 2, 3, 1, 2, 3. Let's dash in those asymptotes. Doot, 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 doot. Now let's go ahead and sketch in this function. Let's figure out if I am positive or negative. Remember, I'm going to have a 0 there, and it's going to cross through. So let's go on the right over here. So say like an x value of 4. Plug that into your function. 4 over 4 plus 3 is positive. 4 minus 3 is also positive. So positive over a positive times a positive is positive. So that branch is up there. Since that branch is starting up, this branch has to start down. I cross over. I have to go up because the multiplicity there is telling me to cross, not bounce. And I don't have any other zeros there. And since that branch is up, this branch is down. So bada boom, bada bing, there is my function, and now I can answer these questions. The limit as x approaches 3 from the left is negative infinity. The limit as x approaches 3 from the right is positive infinity. The limit as x approaches negative 3 from the left is negative infinity, and the limit as x approaches negative 3 from the right is positive infinity. Let's find this limit and recognize that this function is the same as 4x over x plus 3 quantity squared. That's how that factors. So let's think about this graph. I have a 0 at x equals 0 right there from that numerator, and I have a vertical asymptote at x plus 3. I don't know why I'm saying like that. Vertical asymptote at 1, 2, negative 3. So sketch that in, and a 0 there. Am I positive or am I negative? Well, this is one of those examples of where you can quickly think about these two functions and where they are positive and negative. That red bit right there is my numerator. I'm going to do my denominator in blue. X plus 3 squared is that graph. So if you think about where this function is positive and negative, we'll notice that the blue graph there is always positive, and the red graph is negative here and positive up there. So when I sketch this function in, I can tell that I'm going to be negative to the left of 0 and positive to the right. So that tells me that I'm going to cruise like that and level out to that horizontal asymptote at 0. And over here, I'm also going to cruise there, but I'm going to stay negative that whole time. So that's my function. But I didn't answer the question yet. I want to know the limit as x approaches negative 3. Well, as x approaches negative 3, the limit is negative infinity, because that branch goes down and that branch goes down. So negative infinity. But do you see why intuiting these functions is actually kind of cool and useful? Yeah, you do. More uber limits here. So let's first off continue to factor this. Notice in the denominator, x squared minus 16, we have a difference of squares there. So that's going to factor as x plus 4 times x minus 4. So we're going to rewrite this function as 3x squared times x minus 5 over, notice now we have 1, 2, x plus 4 factors. So I get x plus 4, quantity squared, and then I also have that x minus 4 right there. So let's now piece all this together. I have a vertical asymptote at 1, 2, 3, positive 4, and 1, 2, 3, negative 4. Oh, whoops, there we go. I have a 0 at x equals 0, and I have a 0 at x equals positive 5. So let's approach this problem in a different way. Let's plug in a point to see where we are. Let's go to the right of that x-intercept right there, which has a value of 5. So let's try 6. If I plug into my function 3x squared with a positive 6, well, that's positive, times x minus 5, well, 6 minus 5 is still positive, over x plus 4 quantity squared, that's positive no matter what x is because it's squared. And then finally 6 minus 4 is also positive. So all those terms are positive. That's telling me to the right here I am positive. But I know that I have to cross at that 0. So since I'm positive to the right, and I know that my horizontal asymptote is going to occur at positive 3 because I have a cubic function over a cubic function, same degree, but I have that coefficient of 3. 1, 2, 3, so I've got that running there. I know, since I'm positive to the right, that my function has to be coming up like that, so that's going to go down. The multiplicity of the vertical asymptote that's giving me the x value of positive 4, well, the x value of positive 4 is coming from that guy, and the multiplicity there is 1, so that tells me that this branch has to be up here. I have to come down and hit that 0, and again, the multiplicity of that 0 now is coming from that guy right there, which is squared, so I have to bounce and turn back up to that asymptote. But since the multiplicity of that asymptote coming from that factor right there is 2, I need to match it. So I'm going to curve out like that. And so now we can answer these limit questions as x approaches negative 4 from the left. My limit is positive infinity. As x approaches negative 4 from the right, my limit is also positive infinity. As x approaches 4 from the left, I am also at positive infinity. And as x approaches 4 from the right, I am at negative infinity. So once you sketch that function in, identifying the limits ain't no thing. We have so many more problems to do. It's going to be a busy day in class tomorrow. Okay, so we want to find this limit, and in order to do so, we're going to need to do some factoring. So let's look at the denominator first off. 5x minus 10. Well, I can factor out a 5, and I'm left with an x minus 2 over my numerator x cubed minus 8. But I'm thinking that I have a factor x minus 2 in that numerator, since I probably have a hole there, since it's just asking for the limit and not a one-sided limit. So let's do some synthetic division. Let's divide by that linear factor, x minus 2. When we do that on this function, x cubed plus 0x squared plus 0x minus 8, let's do some synthetic division. And it goes quickly with these problems. Notice 1, 2, 4 is telling us that I have my x minus 2 factor, and I'm also left with x squared plus 2x plus 4. And it's just that quick to do those problems. X squared plus 2x plus 4. So notice we have our hole there. So now we can look at the limit as x approaches 2 of x squared plus 2x plus 4 over 5, and we can directly substitute in 2. So we get 2 squared plus 2 times 2 plus 4 all over 5. Well, 2 squared is 4, 2 times 2 is 4, and 4 is 4, so I have 4 times 3 up there, which is 12 over 5. That is my limit. Apparently we're doing one more function sketch again. So let's factor that denominator. I can go 3x. I can pull out a 2, so I'm left with x squared minus 4. Hopefully now you recognize it as a difference of squares. So we get 3x over 2 times x plus 4 times x minus 4, like that. So I know I have asymptotes at positive 4 and negative 4, like there. I know I have a 0 right there. So again, let's think about these two functions. And again, we can kind of intuit where our rational function needs to be. Well, 3x, that is a linear function, so it's shooting off like that. Think about that function, the denominator, that's a quadratic, x plus 4, x minus 4. Those represent x-intercepts of positive and negative 4. And I can sketch that function in. It's going to look something like that. So again, I can tell then that over here, both branches are going to be positive. So my function is going to be positive there. I'll use a different color. So let's undo that and go black. I'm going to look like that. And then in this section here, between that asymptote and the 0, notice red is positive and blue is negative. So that tells me I'm going to be negative there, going up to that 0. The multiplicity of the 0 is 1, so I'm crossing. And now notice to the left of that, red and blue are both negative. So a negative times a negative is a positive, so I have to be going up there. And then finally, over here, in this section over there, red is negative, blue is positive, so I am down like that. So an interesting way to look at these functions, intuiting them as such. So explain what is meant by a removable discontinuity and a non-removable discontinuity. Well, a removable discontinuity is a hole. A non-removable discontinuity is a vertical asymptote. Write a function g of x that has a non-removable discontinuity. So something with a vertical asymptote, well, how about 1 over x? That'll do it. How about a function h of x that has a removable discontinuity? Well, a removable discontinuity is a hole. So how about x over x for h of x? That has a hole at 0. And finally, a function p of x that is continuous for all values of x. Well, how about we just say the function x? Those are the 3 most boring examples you could ever come up with, but they all satisfy that criteria. Alright, so let's sketch the function that has all of these lovely, lovely characteristics. So first off, limit as x approaches negative infinity is 3. That's telling me that out to the left, I have a horizontal asymptote at 3. So I'm going to dash that in as such. Limit as x approaches positive infinity is negative infinity. So that's essentially telling me that to the right, my end behavior is down. So I'm just going to remember that. And so keep in mind that's a little different than a horizontal asymptote. Maybe we have some sort of oblique asymptote, or maybe it's just some polynomial function with a negative coefficient going out to the right. I don't know. But I do know that the limit as x approaches negative 5 is 0, which tells me at 1, 2, 3, 4, negative 5, right there. I'm going to redo that. There we go, that's better. It tells me at negative 5 I have a 0, so I'm going to draw that in. As x approaches negative 2 from the left, my limit is negative infinity. So from the left of negative 2 there, I'm going down to negative infinity. So I know that's going there. I have that 0 and I'm leveling off, so I have that behavior already. As x goes to negative 2 from the right, I'm also at negative infinity. So that branch there is down. Let's see, as I approach 1 from the left, my limit is positive infinity. So at 1 there, I have another vertical asymptote. And it doesn't tell me where I need to cross, so I'm going to cross somewhere and curve up like that. As I look at 1 from the right, my limit is positive infinity. So again, I'm up there. And now it gets weird. Limit as x goes to 3 from the left is 2. So from the left, when I go to the x value of 1, 2, 3, from the left, I need to be coming down to that value of 2 right there, which is coming right there. And notice I drew it as an open circle because I don't know the value of the function. But I do know the limit from the right is negative 4. So if I go down to 1, 2, 3, negative 4, from the right, I know my function's coming into that. And remember, my end behavior is down, so this function is going to continue to go down like that. And this is my lovely, lovely function. So now let's do the opposite idea there. Let's write a function, f of x, that fits these characteristics. The limit as x approaches 2 exists, but the function does not exist. And we're being told that we want this to be a non-removable discontinuity, which again is a vertical asymptote. So to get a vertical asymptote, I'm going to put a factor of x minus 2 in the denominator because that gives me a vertical asymptote at 2. And I also want the limit as x approaches infinity to be positive 4. So I need to throw a factor in my numerator. So instead of calling that 1, I'm going to call it x, because now the degrees are the same. So the function will have an asymptote at 1. And now if I multiply this by 4, my function will have an asymptote at 4. And I will still have my vertical asymptote at positive 2, a non-removable discontinuity. So compare that to this one. This time I want the limit of the function as x approaches 2 to exist, but I don't want f of 2 to exist again, and I want this to be a removable discontinuity. So this time I need to create a hole. So I need to go x minus 2 over x minus 2, like that. And now I want the limit as x approaches 3 to be 0. So I'm essentially saying I want a 0 at 3. So 0's coming from your numerator. I need to write a factor, x minus 3. And now I've ensured that I have a removable discontinuity at 2, a hole. And I will have a 0 at 3. So I am happy. I can make it as complicated as I want, but this is the basic function that will get us there. Now let's do one more little f of x problem. I want the limit as x approaches negative infinity to be negative infinity. Well, again, let's stick with the idea of using the easiest function we can. How about negative x? That function looks like that, so I'm realizing I'm a liar because I said I want the function as x approaches negative infinity to be negative infinity. So that needs to be positive x so that my function looks like that. Down to the left, we're essentially just talking about end behavior. Whew. So that was a lot of problems we just looked at, and my voice is tired from talking to you. So think about what you still need to do to prepare for this test. Get that study guide done and be the rock star that you are.